So, in the previous lecture on tensors, we looked at the introductory concepts related to tensor of order 2, which we will call most often as tensors itself, and we saw that the overall scheme in which we describe and define these tensors is identical in the sense that tensor of order 0 and tensor of order 1 and tensor of order 2 can be defined analogously, and in more common terms we know the tensor of order 0 to be scalar and order 1 to be vector. And so, now having defined these quantities in the previous lecture, now we can look at some of the operations with these vectors and tensors, and we will begin by first summarizing quickly what are the different notation types which can be used. So, the notations which are used for describing the governing equations are basically two types. The first one is the boldface notation, in which case of course we in the governing equations the scalar variables or properties which are also scalar are used in italicized font, and so we have again my this thing. So, I have to start again
from this one.
Oh, okay, this one, okay. I think whenever the wire touches the hand, then there is noise. So, the notations which are used for governing equations basically belong to two different types. The first is the boldface notation, in which case the scalar quantities that we use or the which could be variables or properties of materials, they are described using italicized fonts, and for example density, viscosity and so on. We also have the vector and tensor variables, as we saw that they are described using the bold typeface, and so bold font is used to describe these quantities, and so we have using which we can describe a governing equation. Alternately, we can also describe the governing equation in what is called an index notation, or it is also referred to as suffix notation or Einstein notation. So, in this case scalar of course again is same italicized font with no index, because it is there are no components of scalar tensor, it is essentially just one quantity. On the other hand, with vector we know that there are three components. So, for example, vector t will be indicated using italicized font ti, which means there are three components of t1, t2, t3, or np which is n1, n2, n3, or vk which is v1, v2, v3, and so these ipk which are the indices which are used to describe the three different component, and basically they take values of 1, 2 and 3 depending on which axis we are referring to or which base vector we are referring to, and therefore they are called dummy indices. And similarly tensors, when they are indicated in this index notation, we use again italicized fonts, two indices, and so d m n or omega p q, and again these k l m are dummy indices, and of course these dummy indices take values of 1 and 2 if we have a two dimensional problem, or they will take values of 1, 2 and 3 if we have a three dimensional problem. So, the governing equation could be described using either boldface notation or the index notation. So, just to look at again and capture why this or that notation is useful, let us look at why is boldface notation used. It is actually very compact, and so we can very briefly and quickly state the governing equation. Another advantage of the boldface notation equation is that it is not expressed in a frame or a coordinate system, and so therefore it is a very general statement of the physical principle. For example, later on we will see that the linear momentum balance and for a Newtonian fluid, these are Navier-Stokes equations, they can be expressed in boldface notation very briefly, and they are just embodying the physical principle that conservation of linear momentum or Newton's second law has to be satisfied by the fluid, and therefore given that they are embodying a physical principle, the boldface notation is very useful in understanding or comprehending physical significance of different terms and different governing equations. On the other hand, when we write the index notation or suffix notation, the idea here is to use a still compact description. This may not be as compact as the boldface notation, because we will have the indices which are also described. So, therefore, the index notation will then allow us to write for each and every component of different governing equation, and generally the indices, the way they are used and the way we carry out operation, the overall expression is in terms of rectangular or Cartesian coordinates, and this terms and equations very easily we can therefore simplify. So, boldface notation is useful for understanding and comprehending more often than not, and if you want to work with an equation and try to simplify and add and subtract and do certain operations, we find that it will be more easier if it is done in terms of index notation. And of course, when we are trying to solve the real problem, the complete governing equations with all the components fully written up can be very lengthy, and it of course will incorporate lots and lots of terms depending on whichever problem we are trying to solve. And of course, given the engineering problem of interest, we will choose a rectangular, cylindrical or spherical coordinate system to actually write all these governing equations. So, in this case this is very particular to a specific problem, and therefore, the overall set of equations are applicable for only that situation. And of course, depending on the problem statement, we could also have a coordinate system which is not the most commonly used, for example, a helical coordinate system. So, when we have polymer processing in which there is a helical screw and flow based on the around the helical screw in a barrel, then maybe helical coordinate system is a more natural coordinate system of choice. So, therefore, the choice of coordinate system is essential to describing the complete governing equations. And of course, we do this because in the end we will have to seek a solution, and this solution could be an analytical solution or it could be a computational solution. So, when we go from top to bottom here, we increase in terms of the overall details that are there in the equations, also the specificity of the equation, and so many times when we do modeling or when we are trying to describe a theory initially, we will use either a boldface or an index notation. When we come closer to solving the problem, then we express either of these two in terms of complete set of governing equations and then attempt the solution. So, this is different types of notations are used in rheology as well, and so we will go back and forth between these notations while describing many of the principles involved or many of the initial problem setting up of the problems, and when it is required for the solution we will always revert back to the complete set of equations and attempt the solution. And this of course always involves solving and specifying the overall governing equations in terms of a particular coordinate system. So, having seen the notations in terms of boldface and the index notation, the basis of all of these is in terms of base vectors. So, since we are describing 3-dimensional space, we have 3 base vectors which are useful to describe, and these 3 independent base vectors, of course their linear combination is used to then describe rest of the space. So, generally when we use the known coordinate systems like the rectangular, cylindrical and spherical, we use 3 unit vectors, and they are will be denoted as in cylindrical coordinate, for example, E r, E theta and E z. And so, each of these coordinate system we have the 3 unit vectors, and we know that these 3 unit vectors are perpendicular to each other, and therefore, the 3 basis set is actually a coordinate system which is orthogonal. Generally, when we use the index notation, instead of specifying, as I said earlier, a specific coordinate system, we use a generic set of unit vectors, and in this case we will indicate them as E and some dummy index I. So, E I would imply that it is a set of 3 unit vectors E1, E2 and E3, and therefore, I takes values of 1, 2 and 3. So, in this kind of a notation using these base vectors, then any vector V can be basically linear combinations of the components and the unit vectors. And so, what we have is description of a vector V in terms of its different components. And so, V1 E1 plus V2 E2 plus V3 E3. Since when I write these quantities, it is difficult for me to have an italics and a boldface. What I will do is indicate a bar, and this bar below implies a vector quantity. So, what we have written here is a velocity vector V. So, basically the bar below the quantity implies that it is a vector quantity. Similarly, when we have a tensor quantity, we have 9 components as we saw earlier. So, Dij, and we can describe them using a dyadic product of these unit vectors, and we will again soon come across this dyadic product again when we look at different operations that are involved in with varieties. And so, we have basically 9 components of a tensor. So, we can express it in boldface notation just as D, or we can express it in component and index notation as D. So, with the notation and the base vectors, then we are now ready to start looking at some of the operations that are useful relating vectors and tensors, because these will be involved in the governing equations or manipulations of governing equations when we solve some of the specific rheology problems. So, one of the first thing, for example, that we might see is a multiplication of a scalar and a vector. And so, in boldface notation, let us say we have this momentum flux basically. So, density multiplied by velocity, and so this is described. So, this will be the boldface notation. Described using index notation by describing this vector in index notation. So, vector V will have to be described in index notation. And we know that if I use let us say M as a dummy index, then V is nothing but summation M V M E M. And so, this multiplicating factor, which is basically rho V M E M. So, this is a multiplication between scalar and a vector quantity, and since rho is a scalar, we could also write this as rho V M E M. So, now in terms of the momentum, this becomes the mth component. So, we started out with a vector, and we can again indicate this in matrix notation also, that we had a vector V1, V2, V3, and then we had a multiplication of rho and V1, V2, V3, which led to a new vector which had component rho V1, rho V2, rho V3. So, this is what is expressed here, and this is what is expressed in this vector V. So, therefore, the multiplication of a scalar and a vector quantity is we have used it various times, and in terms of index notation, rather than writing in terms of V M E M like this or V M E M with the summation sign this way, what we quite often also do is just write it as V M. So, whenever we have a quantity with one index, we know that it is a vector quantity. So, therefore, in a Gavani equation, if we have the quantity being expressed as rho v j, and j is the only index, we know that this is a multiplication of a scalar rho and a vector v j, and since scalar and vector are being multiplied, now rho v j is the jth component of the vector rho v j. So, therefore, this is again a vector quantity, and of course, just to summarize, these are all dummy index. So, we can use any one to signify, and we know all of them will go from 1 to 3 for a 3 dimensional situation. So, now we also have other sets of operations. For example, we have additions of 2 vectors, and again these can be written in an index notation. So, if we have let us say a vector A and a vector B being added, again this is boldface notation. And then we can describe this as AP plus BP. So, again because we have the same index, we know that these two are going to be summed, and first component of A is going to be summed with first component of B, and so on. So, this is the index notation. And just to write this in matrix notation also, we have the 3 components, and then we have the 3 components of and of course, we know the result to be A1 plus B1, A2 plus B2 and A3 plus B3. So, basically this is what is being written here and in index notation. So, clearly what you can see is the key thing here is to use the same index, for both A and B, and this is because the same index is being used because we have basically same index which sum each other. So, therefore, it is important for us to recognize that whenever we are looking at one particular component, we should make sure that in the Gavani equation we actually take the same component throughout. And it is given that these are dummy indices, if it is written like this or if it is written like this, both of these are completely identical, because P and I are only dummy indices, and therefore, both of them go from 1 to 3 and both of them indicate exactly the same thing. So, as you can see, the P and I's and the dummy indices are there only to represent the vector quantity in index notation. They by themselves do not signify anything particularly. Now, the next operation which we can look at is a familiar product, which is the scalar or the dot product between 2 vectors, and in this case we know that the result is A1 B1 plus A2 B2 plus A3 B3, and this is we can write down, we can do this again simplified notation. We can try to say that it is A is nothing but AI times EI, and then this has to be a dot product with, let us say, B, which is another vector. So, we use another index because now these two are 2 different vectors, and so now this operation has to be carried out, and so this we can carry out because now A and B, these are components, and then therefore, they can be involved in terms of what we can do is we can involve the vector operations, vector quantities, and remove A and B. So, this overall thing can be written as summation of I summation of j a I b j and then E I dot E j. So, basically because vectors are only involved in the dot product operation, the unit vectors are involved, and therefore, we do not really have the scalar components involved, and scalar components can be taken out. Now, since it is an orthogonal coordinate system, we know that if it is the same unit vector, then the dot product is unity, because it is a unit vector. If we are talking about two different unit vectors, then the dot product is actually 0. And just to look at, for example, if we have E x and E y, E dot x and E dot x is of course equal to 1, but E dot x with E dot y, because they are perpendicular to each other, is 0. So, therefore, this E dot I dot E dot j is expressed briefly in terms of what is called a Kroneker's delta, and this has the property that it is 0 if I is not equal to j, and it is 1 if I is equal to j. So, you can see that if I is equal to j, then we have it equal to 1, and if I is not equal to j, then we have it to be 0. So, now just going back and reminding ourselves that what we are looking at is a scalar dot product of two vectors, and so now if we carry out this operation, and so now what we saw is we can write the overall dot product A dot B as summation over I summation over j as A I B j delta I j, and given that this delta I j quantity is only 1 when we have I is equal to j, we can as well replace I and j. So, therefore, we can write this as summation I over summation A I B I, or we could also write this as summation j A j B j. Because of delta I j being unity only when I is equal to j, we can actually replace them with each other. Quite often the summation signs that we wrote here are not usually written. So, these summation that we wrote are not written. Okay. So, okay, so the summation which we have written, the summation sign itself are not really written, and so what we end up doing is write some of these equations. An example again. So, if it is in boldface notation, we are looking at A dot B. So, what we could quickly do is just write this as A I E I dot B j E j, and just to sort of make an emphasis that I and j are dummy indices. So, let us I even have the flexibility of just using any other index also. So, I will use M and P. So, B P E P, and since these two are involved in the dot product, this could immediately be written as A M B P delta M P, and since we know that delta M P is unity only when M is equal to P, I can write this as A M B M. And what you can see in the discussion so far is actually whenever an index is repeated, it implies a summation. So, in for example, if we look at this here, you have I being repeated and summation is involved, here j is being repeated and summation is involved, here again I is repeated and summation over I is there, or j is repeated and summation over j is there. So, basically when we have this AM BM, it automatically implies that there is summation, and so if we have to write this completely, since M takes values of 1 2 3, this term would be equal to A1 B1 plus A2 B2 plus A3 B3. So, therefore, in index notation A dot B is just written as AQ BQ, where Q is the dummy index. So, and this of course we know is a scalar quantity, and therefore, this product the summation of 3 terms is a scalar quantity. So, therefore, what we have seen are examples of operations with vector quantities, and we saw this A and B. Now, there is also a dyadic product of 2 vectors, in which case 3 components of A and 3 components of B together will lead to a dyad, and this dyad has 9 components. And so, the gradient of velocity for example is a dyad, or also in momentum equations we will have a dyad which is related to the velocity. So, this is a in terms of the inertial terms, in linear momentum balance we will have a dyad involved. So, the AB dyad is a similar dyad which has 9 components, similar to a tensor. And in fact, when we expressed the tensor Tij as Eij, in fact, what we had written here was a dyad. So, with the unit vectors Ei and with the unit vectors Ej, we form a dyad, and these are again 9 components of dyad, and using those 9 components we can describe the 9 components of tensor. So, therefore, what we have seen in this lecture so far are operations with scalars and vectors. Of course, many of these operations we are already familiar with, and so we using index notation we can in a compact manner describe these operations. The cross product is described using again a compact notation as epsilon ijk ai bj. So, what this implies is of course this is a vector quantity, which means there are 3 components, and in this expression if you see I and j are repeated, and so the k is actually gives you the 3 components, and when we write each and every component we have to have I and j go from 1 to 3, and the epsilon ajk, which is called the alternator, has a property that it is 1 if ijk is 1 2 3 3 1 2 or 2 3 1, and it is 0 if any two indices are equal, and it is -1 if I j k is 1 3 2, 3 2 1 and 2 1 3. So, therefore, using this definition, in fact, you can work and find out the expand this notation and see whether you get the usual answer that you know for a cross product of two vectors, and what we will usually get is a 1 b 2 minus b 2 a 1 e 3 and so on. So, what we know generally as cross product can be expressed very briefly using index notation using the alternator. So, with this we will stop in this particular lecture. In the next lecture we will see the operations with tensors and also some operations involving derivatives. Derivatives may be with respect to time and derivatives with respect to space. We have the gradient operator as well as the divergence operator, and in the course on rheology all of these derivatives with respect to time and space will be very useful. So, again it will be useful to know how they are expressed in boldface notation as well as in index notation.